Hi students, welcome to my channel. Myself is Vedamurthy. You are watching chemistry class 11 and first PU chapter 4 chemical bonding and molecular structure. This is the fifth video of this unit 4. Today we are going to discuss about the polarity of bond VSEPR theory in detail. The existence of a 100% ionic or covalent bond which represents an ideal situation. In the reality, no bond or a compound is either completely covalent or ionic. Even in case of covalent bond between the two hydrogen atoms, there is some ionic character. When covalent bond is formed between the two similar atoms, say for example H2, O2, Cl2, N2 or F2. In these examples, the shared pair of electrons is equally attracted by the two atoms. As a result, the electron pair is situated exactly between the two identical nuclei. So the bond so formed is called non-polar covalent bond. Contrary to this, in case of a heteronuclear molecule like HF, the shared electron pair between the two atoms gets displaced more towards the fluorine atom. Since the electronegativity of fluorine is far greater than hydrogen, so the resultant covalent bond is a polar covalent bond. As a result of polarization, the molecule possesses the dipole moment, which can be defined as the product of the magnitude of the charge and the distance between the centers of the positive and negative charge. So dipole moment can be written in the Greek letter micron. 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 So this is nothing but a dipole moment. Dipole moment can be written as micron. Okay. So here we can express it in mathematically this micron unit dipole moment. So it can be represented as dipole moment micron is equal to this is dipole moment charge, that is q, charge q into distance of the separation r. Q into micron is equal to Q into R. Here Q is the charge and R is the distance of the separation. So dipole moment is expressed in dB units. Dipole moment we can express in the units dB units. Dipole we can say dB units, that is D. So 1D is equal to 3.33564 into 10 upon minus 30 cm. Okay, so what is this 30 cm? What is this cm? So C is the coulomb and m is the meter. C is the coulomb and m is the meter. So further dipole moment is a vector quantity, and by convention it is depicted by a small arrow with the tail on the negative center and the head pointing towards the positive center. Say like this. Okay, this is the arrow which can be vector quantities. In the dipole moment we can write it in this position. So here, but in the chemistry, the presence of the dipole moment is represented by the cross arrow. So the Levy structure of the molecule, the cross uh, is on this arrow cross. See, the cross on positive side, this is on positive side arrow towards on the arrowhead towards on the negative side. Okay. So for example, HF we can write it like this. HF, H dash F, there are valence electrons, 6 valence electrons. So here we can write it as like this. This is the dipole moment of HF. So this arrow symbolizes the direction of the shift of the electron density in the molecule. So note that the direction of the crossed arrow is opposite to the conventional direction of the dipole moment in vector. So in case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of the bond, so known as the dipole bond dipole, so but also on the spatial arrangement of the various bonds in the molecule. In such case, the dipole moment of the molecule is the vector sum of the dipole moments of the various bonds. For example, in water molecule which has a bent structure, in water molecule how we can write it, this is the way we can write H dash O dash H. Here the dipole moment is towards like this and dipole moments towards like this towards O. So this is the bond dipole. So same way we can write it for the resultant dipole moment. So we can write the dipole moment is the reverse of that, H dash O dash H. So this is towards dipole moment. This is the dipole moment of the water molecule. Here the dipole moment of the water molecule, net dipole moment of the water molecule is equal to how much? So net dipole of the water molecule is equal to 1 micron, that is 1.85 d, 1 dB. So what is the d? D is equal to 1.85 into 3.33564 into 10 upon minus 30. So total net dipole moment of the water is 6.17 into 10 upon minus 30 cm. Okay. So the dipole moment in case of BeF2, how it will be is 0. In case of BeF2 it is 0. Why? I will tell you. F dash Be dash F. Here the dipole moment is like this. So both are opposite. This is because the two equal bonds dipole points in opposite direction. Hence, so it can cancel the effect each other. So the dipole moment of the BeF2 is 0. Dipole moment of the BeF2 is 0. Okay. So see here, this is the example here. BeF2 is 0. Dipole moment of the BeF2 is 0. Total dipole moment. Okay. So in tetraatomic molecules, for example, BF3, what will happen? So the dipole moments is also here 0, although the B dash F bonds are oriented to an angle of 120 degree Celsius. Sorry, 120 degree, and the angle of 120 degree. So the three bonds moments gives a net sum of the 0 dipole moment as a result of any two is equal and opposite to the third. So these are, so it is 0. BF2 is 0. So BF3 molecule represents the dipole moment is 0. So now let us study on the interesting case of ammonia NH3 and NF3 molecules. So both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom. This is the examples. So although there is a fluorine is more electronegative than nitrogen, the resultant dipole moment of ammonia is 4.9. Resultant dipole moment of the ammonia is 4.9 into 10 upon minus 30 cm, which is greater than that of NF3 is a 0.8. NF3 is 0.8 into 10 upon minus 30 cm. So because in case of NH3 or ammonia, the orbital dipole due to the lone pair is in the same direction as the resultant dipole moment of the N-H bond. N-H bond. So whereas in NF3, the orbital dipole is in the direction of the opposite to the resultant dipole moment of the three molecules N-F bonds. The orbital dipole, because of the lone pair, decreases. The effect of the resultant NF bond moments, which results in the low dipole moment of NF3. So we can write it as like this. Okay. So now we will see that different dipole moments of some of the selected molecules. For example, AB. If the type of the molecule is AB, the examples belongs to hydrogen fluoride, hydrogen chloride, HCl, hydrogen bromide, hydrogen iodide, and H2. So various atoms, HF for example 1.78 is the dipole moment and its geometry is linear. So in the AB, whatever the molecules are linear and its dipole moment is tabulated here. So next example is AB2. In the type of AB2 molecules, here AB2 is H2O, H2S and CO2. Here the dipole moment is 1.85, 0.95, 0.0 is. So because both are opposite direction. So bent linear structure. Geometry is linear, bent. So molecules AB3 having the examples NH3, NF3, BF3. Here the dipole moment is 1.47, 0.223 and 0 respectively. The geometry of the shape of the molecule is trigonal, pyramidal, and trigonal planar. So molecule AB4 having the examples methane, CHCl3, CCl4, carbon tetrachloride. So methane is 0 and carbon tetrachloride also 0. CHCl3 is 1.04. CHCl3 and CH4 having the geometry is tetrahedral. Okay. So here, just as all the covalent bonds have some partial ionic character, the ionic bonds also have partial covalent character. The partial covalent character of the ionic bonds was discussed by Huygens in the terms of the rules like the smaller the size of the cation and the larger size of the anion, the greater the covalent character of the ionic bond. The greater the charge on the cation, so greater the covalent character of the ionic bond. So for cations of the same size and charge, the one with electronic configuration n-1 into d to the power n ns0, a typical of the transition metal, is more polarizing than the one with a noble gas configuration ns2 np6. So typically of alkali and alkaline earth metals cations. The cation polarizes the anion, pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. So this is precisely what happens in a covalent bond is the buildup of the electron charge density between the nuclei, the polarizing power of the cation, the polarizability of the anion and the extent of the distribution. So polarization of the anion or the factors which determine the percent covalent character of the ionic bond. Now let us discuss about the valence shell electron pair theory. Valence shell electron pair theory, that is VESEPR theory. So we already discussed about the Levy's concept, which is unable to explain the shape of the molecules. But this whisper theory provides a simple procedure to predict the shape of the covalent molecules. This theory was studied Sidwick and Powell in 1940. They proposed the theory based on the repulsive interaction of the electron pair in the valence shell of the atoms, and it further developed by the Nylam and Gillespie in 1957. There are some main postulates of the whisper theory, or the shape of the molecule depends upon the number of valence shell electron pairs are bonded or non-bonded. It may be bonded or it may be non-bonded around the central atom. And second one, the pairs of the electrons in the valence shell repel one another since their electrons clouds are negatively charged. Third one, so these pairs of the electrons tend to occupy such positions in space that minimize the repulsion and thus maximize the distance between them. And the fourth is the valence shell is taken as a sphere with the electron pairs which is localizing on the spherical surface at the maximum distance from one another. The fifth one is the multiple bond is treated as if it is a single electron pair, and the two or three electron pairs of the multiple bond are treated as a single super pair. The last one is sixth one is postulate of the sixth one Vesper theory. So when two or more resonance structures can represent a molecule, the Vesper model is applicable to any such structures. The repulsive interaction of the electron pair decreases in the order lone pair. I will write it here like this. So lone pair minus lone pair is more than lone pair minus bond pair. So again, which is more than bond pair minus BP minus BP. That is BP is bond pair minus bond pair. Okay. So Nylam and Gillespie 1957, they refined the Vesper model by explaining the important differences between the lone pairs and the bonding pairs of the electrons. While the lone pairs are localized on the central atom, each bonded pair is shared between the two atoms. As a result, the electron pair is electrons in a molecule occupy more space as compared to the bonding pairs of the electrons. So this results is in a greater repulsion between the lone pair of electrons as compared to the lone pair minus bond pair and bond pair minus bond pair repulsions. So these repulsions affects the results in the deviations from the idealized shapes and the alteration which is based on alteration in the bond angles in molecules. For the prediction of the geometrical shape of the molecule with the help of Vesper theory, it is very convenient to decide the molecules into two categories. Divide the molecules into categories. So one is molecules in which the central atom has no lone pair, and the molecules in which the central atom has one or more lone pairs. Here in the table we will going to discuss some of those things. See, here there is an arrangement of the structure BeCl2, Bf3CH4 and CpCl5. The shapes of the molecules in which the central atom has no lone pair electrons. The Vesper theory is able to predict the geometry of a large number of molecules, especially the compounds of the p block elements, accurately. It is also quite successful in determining the geometrical quite differences between the possible structures as very small The theoretical basis of the VSEPR theory model regarding the effect of the electron pair repulsion on molecular shapes is not much clear, and there is some doubts or it there in the VSEPR theory model also. So here the table, the geometry of the molecules in which the central atom has no lone pair of electrons is this is the 180-degree linear. So there are number of electrons in the uh, molecule is 2. The arrangement of the electron pair is like this. This is linear, and the molecular geometry is B dash A dash B, that is linear. Some of the example is BeCl2 HgCl2. So there are like that number of electron pairs is 3, and the trigonal planar is the arrangement of the electron pair, and its molecular geometry is this is one, and the example is Bf3. The third one is a number of electrons is 4, electron pair is 4, having the geometry arrangement of the electron pair is at 109.5 degree angle. So this is the tetrahedral, molecular geometry is tetrahedral, and the examples are CH4 and NH4 plus. So same there is number of electron pairs is 5, that is trigonal bipyramidal, example is PCl5, and the number of electron pairs is 6. So we'll get the octahedral geometry or octahedral shape. So example is SF6. And the so next there are one more table is here. So this is depict the shapes of the molecules containing the bond pairs and lone pairs. For example, AB to E molecule type is AB to E. Now there is number of bonding pair is 4. Bonding number of bonding pair is 4, and the number of lone pair is 1. The arrangement of the molecule is O double bond S double bond O. This is the way. So what is the reason to know how the shapes are acquired? As there are some theoretically the shape should have been triangular, so planar. Actually it is found in a bent or V-shaped or reverse V-shaped. The reason being the lone pair bond pair repulsion much more as compared to the bond pair minus bond pair repulsion. So the angle will become so under 19.5 degree. So same example AB3E, you can see these examples, all the 4 examples. These are very important. You can see, refer this is. I hope students, this is I'm ending this video with this one. Thanks for watching this video.